At this point, we should already have a pretty good grasp of what a limit actually means, but I want to take a couple minutes here to look at the definition of a limit and kind of talk about how we formally define this. This formal definition of a limit is actually what allows the rest of calculus to work the way it does. So it is an important idea, and you're not necessarily going to need to know this definition, but you do need to understand how it works because it is the foundation for the rest of calculus. So in this formal definition of the limit, essentially what we have is we have a function, and the limit of that function as x approaches some particular value c is a number r if f can be made arbitrarily close to r by taking x sufficiently close to c. And I want to talk about what those terms mean in a minute, but not equal to c. So this is an important idea here that we don't really care what happens at c for our function f. We don't care what f of c is. We care what happens in the neighborhood around c. So if that limit exists, we have this notation that we're going to use here for limits. So let's look at a graph and kind of talk about how this definition ties into what a graph of a function is going to look like. So in this graph, along the x-axis here, I'm going to put the value c. So this is the value that x is approaching. By the way, we could use other variables besides x and limit. So we could have t approaching some value or theta approaching some value. That's just going to be whatever variable this horizontal axis is here on a graph. And then the values of the function itself are plotted along the y-axis. So we're going to have f of x here. And so I'm going to note this y value here where the hole in the graph is, and I'm going to call that r. So the idea of the limit is if we are taking values of x that are getting closer and closer to c. All right, so along the x-axis, we're plugging in values of x that get closer and closer to c. Then that means that the values of f of x, which are the values along the y-axis, are going to get closer and closer to r. Now, let's talk about what this arbitrarily close and sufficiently close mean. So let's say that r is 2, all right? And I know that the value of the function might never equal 2, but I want to get it really close to 2. So when I say arbitrarily close, what that means is if I set a threshold and say I want it within 1/1000th of 2, so I want it somewhere between 1.999 and 2.001. All right, so that's a threshold that I want the values of the function to get within that. What I can do then is choose a value for c. As long as I get within a certain range of c here, it might be kind of a small range, it might be a bigger range depending on the function itself, then I can get values of f of x that are between these two values here. So as we're approaching c from the left, notice that in this particular graph, we're approaching r from above, so I'm going to be getting values that are a little bit bigger than 2. And at some point, all of the values I get are going to be less than 2.001. So they're still going to be bigger than 2, but they're going to be less than that. The arbitrary part comes in as if I can pick really any threshold I want. So instead of 1,000th, let's say I want a millionth. So if I want it less than 2.000001, but still greater than 2, then I can pick a value of c or x close to c so that we get that. So the idea is no matter what threshold I set, I can always get at least that close to r by getting values close to c sufficiently close. And at some point, every number that we plug in closer than that is going to be within that threshold that we set. So this is kind of an informal way of describing this. In more advanced calculus classes or in other calculus classes, a lot of times when you take one in college, you'll see epsilon delta definitions that are a little bit more formal and a little bit more analytic or algebraic. So you use epsilon and delta to represent the distance from C along the x-axis and the distance from R along the y-axis. We're not going to get into those formal definitions here, but this gives us the idea that epsilon delta definition gives us, but more of a verbal approach to it.